In this video, I'm going to talk about how we use the dot product to find something that comes up a lot in physics, which is a term called work. So if I have a mass and I apply a force to it in one direction and it moves in another direction, then the work that is done is equal to the force times the distance, or the change in distance. Change in distance is also often called displacement as well. The shorthand way to write that is W equals F times D. And I should add a little vector. Well, it's not really a vector yet. I'll just say equals the force times the distance. So let me draw a little picture for you. Here's my artistic talent right there. Yep, pretty sweet. You may say to yourself, well, how can I have a force go one way and the direction of movement be another way? Well, the easiest way to think about it is actually how they moved things back before we had vehicles. They did this a lot on the East Coast, where they would have a canal. You know, they've got a lot of water on the East Coast, so they have a canal. And they would have this boat that would sit in the canal, and they'd fill it up with stuff, and then they'd pull it with a horse. So they would attach a rope to the boat, and they would pull it along, and a guy would, or a person would stand in the back of the boat with a rudder or oar of some sort and steer it to make sure that it didn't hit the edge of the canal. But it was a really fast and efficient way to move things. And the force that was being applied to this thing was in a direction like that. So the force vector was not in the direction of movement, because the direction of movement would be this way. So the way that we do this force equals or work equals force times distance is I take the direction of, or I take the component of the force in the direction of the movement. So if this was the force vector, it could be broken down into, we can call it an x vector and a y vector, and we just take the length of the x vector, that is the actual force that we do, times however far it goes. That's my distance or my displacement, and that gives me my work. So let's do a quick example. Hopefully that helps you contextualize it a little bit. If you wanted to Google this scenario and watch a video, you can see a horse pulling a video. So the first one we're going to do is we're going to do it without vectors, although it'll have an angle. So say I've got, let me switch colors. Say I've got a flat surface like this, like the one that I drew above. And I've got some block that I'm pulling, and we apply this force equal to 70 newtons. And my angle here is, let me, hold on. Vector there a little bit to make it more accurate to what I'm going to put right here. Say this angle right here was 60 degrees, right? So I'm pulling sort of almost up, but I'm still pulling to the right here. So this block is going to move to the right. What I need to do is take the component of this force that that is parallel to the direction of movement. Oh, sorry, I should also add, let's move it 100 meters. So that means that my delta D is equal to 100 meters, or my delta X, displacement, whatever you want to call it. So what I need to do is take the length of this red vector and multiply it by the change in distance, which is 100 meters. So force equals, what is that? Well, here I've got 60 degrees. This is the adjacent side. So it is 70 cosine of 60 degrees times, what's my delta distance? Remember, work equals force times distance. And I got to take the force parallel to movement, which is that red line there. So 70 times 60 degrees is the force part. And then the delta D is 100. So 70 times 6 cosine of 60 is a half. So that's 70 times a half times 100, which gives me 70 times 50, which is 3, 5 with 2 zeros. So, and the units for this are Newton meters. And that should make sense because force was measured in newtons and the delta distance was measured in meters. So, bam, simple example. My next one is going to have vectors. Actually, I take that back. My next one is going to be doing the same problem, but with vectors. So, let me copy this. Oops. Right, so same problem, but with vectors. So what I'm going to do is write f equal to the vector. So I'm going to write it in xy component form. So using some quick trig, the x component is going to be 70 times a half, and the y component is going to be 70 times root 3 over 2. I did that sort of this 70 times a half is the same thing I was doing before, where I used the cosine of 60 degrees, and root 3 over 2 is the sine of 60 degrees. That gives me the vertical component because that's the opposite side. So my force vector is equal to 70 over 2, comma 70, I don't want to write this, 70 root 3 over 2. The distance vector is equal to 100 in the x and 0 in the y. So what I can do from there is just instead of doing the work that I did above, my work is always going to be the force vector dotted with the distance vector, or the change in distance vector, displacement vector. So what is that? That is 70 over 2, comma 70 root 3 over 2 times 100, comma 0. And then that gives me, when I do my dot product, this times that is 70 over 2 times 100, plus this times that is just 0, which, notice this number here is the same thing that I had over here, right? So I wound up getting the same 3,500. Say, for example, this was like a flat surface and it had like a channel, and I went, let's take a little blink. So I went like this, and that was 100, and then the channel went up right there, and that was 20. Well, what I can do is this new change in distance vector, the 0 here, would get replaced with a 20, right? And from there, I would do my work equals force vector times change in distance vector, and I would get 70 over 2, comma 70 root 3 over 2, dotted with 100 would be the change in x there, and 20 would be the change in y. And imagine this as like a flat surface. Imagine up is coming out of the board. So just like kind of ignore gravity and stuff like that, and we're pulling with that direction, right? Don't think of it as like up is vertical movement there. Think of it as on a plane. So you could do this, and this would give me 3,500 for that first dot product, plus 70 times 2 is 14 with 2 zeros, root 3 over 2, which would give me 3,500 plus 700 root 3. And that would be the work done. I should specify this. That is the work done by this force to move it from here to there. That will work all the time. What it does is it takes the force times distance in the y component, which would be these guys, and the force times distance in the x component, and it adds them. So I think hopefully you see how doing that dot product sort of simplifies work that would be more complicated. So let me give you one more example. I'm going to write it out. Okay, so this one's sort of abstract, but it is three-dimensional. Say I've got some force 3, 4, 5, so 3 I hat, j hat, k hat, and I want to, I move an object from the point P 2, 1, 0 to the point Q 4, 6, 2 in 3D space with that force. And I want to know how much work is done by that force to make that movement. Well, F is equal to 3, 4, 5, and my distance vector is equal to, what's that change in x from there to there? It's 2. So 4 minus 2. And then 6 minus 1 is equal to 5. And then 2 minus 0 is equal to 2. So my distance vector is that. So once I get that distance vector there, I can quickly say the work is the force dotted with the distance, which is going to take the correct components of the force and apply them to the correct components of the movement of the distance, and add up to the total work done. 3, 4, 5, dotted with 2, 5, 2, which gives me, all right, the first product is 6. The next product, 4 times 5 is 20. And then the last product, 5 times 2 is 10. So what do I get? I get 36. And this is like a unitless problem because I didn't really give any units for any of the parts of the question up here. So where are we going with this? Well, work is just force times distance. That would be like one-dimensional movement without thinking about vectors. I could also say work is a vector f dotted with a distance vector. That's what we just went over. Now, let's tie this to calculus because it is multivariable calculus. Another way that I can multiply force by distance, distance is the integral, displacement is the integral, maybe I'll write this. Displacement is the integral from t1 to t2 of v of t dt. So that means that I can get this guy out of integration. So what if I wanted to calculate my work? What if my force vector was changing over time and that velocity was changing over time? Well, I can do the integral from t1 to t2 of force at any given time times velocity at any given time dt. Because you should see that with this integration here, the force is just going to stay as the force, and integration is essentially multiplying. We've talked about that a lot. So when I multiply velocity by time right here, that gives me a distance. And I'm integrating from t1 to t2, so I can actually find the work in a much more complex scenario if I use integration. And now keep in mind, this is still one-dimensional movement here. What if we were to bump up to 2D or 3D? Well, and this is what we're going to get at like way down the road in this course. It's called a line integral. Work is equal to the integral, I'm going to write over C, and I'll explain what that is if I have time, of f of t a vector dotted with v of t a vector with respect to time. Now, this vector, is, there's ways we can figure it out and the ways we can model it, but the C is, say, and I'm just going to talk about in 2D space, right? So say something starts here and goes along like this, right? And then ends here, right? Well, that path, I call it a C. So the path is defined by C. So the integral over this path of the force at any given time at that spot multiplied by the velocity at any given time at that spot gives me the work. And this may sound sort of confusing. It probably should because there's a lot more to it than just what I'm saying right here. But hopefully this helps you see that why I care about work and force and distance when we're doing multivariable calculus, because it becomes a really good application in a practical sense, and I can do it in 3 dimensions too. This is just in 2 dimensions of what's called a line integral, which is something that we will do later. Thanks, y'all. I will happily answer questions about this in class if you have them.